All right, we're on our last video for limit applications. So let's move away from that algebra and over here to one more Canvas question. So let's translate this limit, this statement into a limit, and then decide if it's true or false. So again, I'll give you a second if you would like to pause the video. All right, so our limit statement is going to be the limit as x goes to 16 from the right of the natural log of x minus 15. And our question is this equal to 0? Well, one of the things we can look at is what is the domain of this natural log function? Because I'm curious about 16. Is it even in the domain? If it's not in the domain, we don't even need to consider it. We know that it doesn't exist. And what we know about natural logs is that we need to have whatever's inside of our natural log to be greater than 0. So if we take that x minus 15, set it greater than 0, we can solve that and get our domain, which is not 0, it is 15. And so 16 is in our domain. So that tells me, okay, why don't I try plugging in uh, 16 into this function and see what we get. We get the natural log of 1, which is 0. So that tells me, yeah, I believe that this is going to be true. Coming from the right-hand side, 216 on this function, we're going to get 0. I do have this function graphed, so here it is. And if we grab a point on our graph here and start dragging it towards 16, we can absolutely see from the right-hand side, we're getting closer and closer to 0. And we are defined there, so we could actually do a left-hand limit or a right-hand limit or even the regular limit, and it's all going to be 0. What's a little bit more interesting is if we look at the right-hand limit going to 15, 15 is not in our domain, but we can take the limit going towards 15, and it's going to negative infinity. We couldn't do a left-hand limit because there's no graph on the left-hand side. We could only do a right-hand limit. So we could also say that the limit, sorry, my iPad got a little crazy there for a second. The limit as x goes to 15 from the left-hand side of the natural log of x minus 15, we could say that that goes to negative infinity. Again, that doesn't exist, but we could talk about how it doesn't exist because that's one of those places where we have an asymptote. So let's take a look at the next one. So similar kind of problem. Let's translate this statement into limit notation and then decide whether or not it's true or false. All right, hopefully you gave yourself a little bit of time to take a look at this. This is going to be the limit as x goes to 4 from the left-hand side of the square root of x squared minus 16. And our question is this equal to 0? So again, we kind of want to do the same thing that we did with that natural log and think about what's going to be the domain of this square root function. And we need for that x squared minus 16, we need it to be greater than or equal to 0. It might help us to factor. It's going to help us a little bit. And sadly, we're not allowed to, set each of these greater than 0. This is not going to give us the domain, so we're going to put a big mark through and we'll highlight it with every color, like do not, do not, do not do this. Where those factors can help us, though, is they can help us draw a graph of this function, x squared minus 16. And we can use that to figure out where it's greater than or equal to 0. And then we'll see why we can't actually do the thing where we set each term greater than 0. I really wish we could do that. It would make things like really easy, but unfortunately, no. But those are our two zeros, and x squared minus 16, that's an upward facing parabola. Its graph is going to look like that. So the x values where x squared minus 16 is greater than or equal to 0 are when x is greater than or equal to 4 or less than or equal to negative 4. So here, our domain of this function is going to be negative 4 to 4. Oops, excuse me, negative infinity to negative 4. I'm writing it and I can't even say what it is. And then 4 to infinity. So our question here is about a left-hand limit. We can't approach this 4 from the left-hand side because there's no graph in between negative 4 and 4. There's just not going to be a graph there. So this is not the graph of the function we're talking about here. This is the graph of what's inside of our square root. The graph of our x squared, our square root of x squared minus 16, what that looks like I have that one graphed here. Let's unselect that, select that. Gotta move this around. Looks like that. And so we can see, okay, we've got a graph when x is less than or equal to -4 or greater than or equal to 4. And if you want to see that x squared minus 16 graph, there it is. So you can see the parts that, right there where it touches the x-axis at -4 and 4, the parts that are above the x-axis, that's where our blue graph exists. The part that's below the x-axis, we don't have a blue graph because it doesn't exist. Those points aren't in the domain of the blue graph. And so there is no left-hand side that we can approach, -4 or 4 from the left-hand side. We just absolutely can't. We can approach it from the right-hand side. We absolutely can do that. And yes, from the right-hand side, it's getting closer and closer to 0. But from the left-hand side, it does not exist. So our statement is false. And the limit as x goes to 4 from the left-hand side, this does not exist. Now, if this was the limit as x goes to 4 from the right-hand side, that would be 0. So we can only approach from the right-hand side, not the left-hand side. This is, we only have that one-sided limit. What you can also say about this is that at 4 and at -4, it only has one-sided continuity. So it's continuous from the right for 4, it's continuous from the left for -4. That's a little deeper kind of into the calculus weeds than we're going to get, but we can really kind of see what they're talking about when you hear statements like that if we're looking at the graph, because we can only approach from the right in terms of that +4 and only approach from the left in terms of that -4. All right, there's one other thing that I would like to talk about in this section, and that is the squeeze theorem. So the squeeze theorem says if we have three functions, f of x, g of x, and h of x, and they're going to be defined for all x, but possibly not at x equaling a. So they could be defined at x equaling a, but we kind of don't care if it's defined or not. It may or may not be. Because we're going to take a limit, remember that it doesn't, if we're actually have a in our domain, it doesn't matter. We could or we could not. It does, so it's got to be defined for all the other points except for maybe that one. And we're going to look at this for some interval containing a. So what we mean here, we've got a picture down here. So there's a. And an open interval containing a, that's us just saying, okay, we're going to take the x-axis and look at it from, like here to here. So we're going to look at it for some range of x values. That's what we mean by an open interval containing a. And it doesn't have to be like symmetric like this. It could be, something, an interval like that, where it's a little closer to a on one side. It's just any interval of x values from x1 to x2, and a is somewhere in the middle of those. So basically, a is in between x1 and x2. And so if f of a is less than or equal to g of x, or f of x is less than or equal to g of x, which is less than or equal to h of x, for all of the x values in that interval, again, we're excluding a because we're taking our limit going to a, so we don't care really exactly what's happening at a. We might be undefined there. And the limits of that bottom function, so that's our lowest function, so that's the bottom slash lowest function, and this is the top function. This is like the upper function or the highest function. If those two have limits that exist as we go to a and they're both equal to L, then the limit of the middle function, oops, I don't want to point to a, I want to point to g. So this is the middle. That limit is also L. So the idea is this is another place in math where we're actually calling this exactly what's happening. We're taking that function g of x that's in the middle and we're squeezing it between two functions. We've got one that's always below it, one that's always above it in that interval that we're talking about. And if those two, the one on the bottom and the one on the top, go to the same limit as you go to a, then the one in the middle has to also go to the same limit. So what this is going to do is make it easy to find the limit for functions that it's difficult to find the limit of. We're never going to have you, at least here in 251, figure out what H and F are, that bottom function and top function. We will actually give you all three. We will ask you questions like, do these three functions satisfy the squeeze theorem? And that's you verifying, yes, this one's on the bottom always, this one's on the top always, and then this guy's always in the middle. And then the limits exist for the ones on the bottom and the top. So we will give you these functions. How this is used, sort of more in practice with mathematicians when they're trying to do limits is we usually have g of x, that middle function, and we're trying to find the functions above and below it so that we can squeeze it in between. But we're not quite there about, with us wanting to do that. So you'll get questions more like this, where we say, okay, we have g of x, it's 4x to the fourth times sine of 1 over x to the fourth minus 2. And then we have two functions that we're going to take a look at. So f of x is going to be 4x to the fourth minus 2. H of x is going to be negative 4x to the fourth minus 2. And I think I labeled these opposite kind of how I wanted them, but it's okay. It kind of doesn't matter which one you call which, because I think this is going to be our function that's on the top, and this is going to be our one that's on the bottom. But it's all right. What we label them doesn't totally matter. And G is our one that's going to be in the middle. So the question is can we use the squeeze theorem? And if so, what's our limit? So what we need to double check is that G of x, so basically is G of x in between f of x and g of x. And again, it doesn't matter which, or h of x, excuse me. It doesn't matter which one is the top one and which one is the bottom. We just need one to be on the top, one to be on the bottom. So let's go take a look in Desmos and see what's happening here. So I've got the three functions typed in there. So f of x, there it is. It's in, 4x to the fourth minus 2. So it's kind of that flattened out parabola. Here is negative 4x to the fourth minus 2. So it's looking like, things are going to get squeezed in there. And then here's our sine function, which is going to look crazy. And it sure does look like those two functions squeeze, that middle function in between them. And that sine function is being quite crazy. If you want to pull away those other two so you can see it, it's oscillating like crazy there in the middle, going up and down and up and down. And it is undefined when x is 0, but it sure looks like that limit is going to negative 2. And so back here, can we use a squeeze theorem? The answer is yes. We've got that h of x is on the bottom of g of x, which is on the bottom of f of x. So g of x is squeezed in between those two functions. And then if we look at those two functions, the limit as we go to 0 of 4x to the fourth minus 2, that's going to be negative 2, because that's a polynomial, so we can do direct substitution. Same with that negative 4x to the fourth minus 2. Sorry, my 0 got a little crazy there. So negative 4 times x, or 0 squared, minus 2. So we get negative 2. So absolutely both of those are negative 2. So we can say the limit as x goes to 0 of this crazy sort of trig slash polynomial function, that's also going to be equal to negative 2. All right, I think that's everything. So where are we at now? You've got a couple of Achieve assignments due on Thursday and Sunday. Our written homework for week 8, which is due on Thursday. Remember, I do not have office hours this week. So let me know by email if you've got any questions. I will try to get to them on Thursday morning. And you've got, the pre-class reading for day 18, which is Monday. I will be back on Monday. And the blank notes for Monday are posted. So on Monday, we are going to look at discontinuities and infinite limits. So, all right, that's everything. Hope you enjoyed our videos, and I'll see you guys when I return.